Okay, so let's start. So yesterday we have seen a counter in which we designed the first sequence. So the question for today is design a synchronous counter using mode control M so that it should count two sequences 7416527, that is sequence number 1, and the second sequence is 6574106, that is when m equal to 1. These are the two sequences that it should count. So a typical application of such kind of design is the running LED lights. So we can have different sequences with a simple mode control. So that is what we are going to look here. Now you can see in both the sequences, in sequence 1, 7416527, the invalid states are 0 and 3. And if you look at the second sequence, 65716574106, in this the invalid state is 2 and 3. So these are the invalid states and these are the valid ones. So we have to now carefully define the next states of these invalid states when m equal to 0 and when m equal to 1. So I want you to start writing down the first two steps. So we are using a D flip-flop. So step 2 would be just the excitation table of D flip-flop. And step 1 is calculation of number of flip-flops using the D flip-flop. So here m equal to 6 and why 6? Because the maximum that we have to count is till 7, and the number of states here are 1, 2, 3, 4, 5, 6, and then again back to 7. So that is why m is equal to 6. In the second one also 1, 2, 3, 4, 5, 6. There are 6. In both the cases, in both the sequences, there are 6 states. So that is why m is equal to 6. And the invalid states are 0 and 3. So we have to design in such a way that their next states are don't cares or 0 if you want to make it lock free. But we will use don't care just to simplify, make the simplification easy. So n equal to 3, where n is equal to the number of flip-flops. Copy this question. I will give you another 2 minutes to copy this thing. Note this valid and invalid states. So this is your sequence 1 and this is your sequence 2. I want this sequence when n equal to 0 and this when n equal to 1. So first one I want when n equal to 0, second one I want when n equal to 1. Like this, if anybody gives you any sequence, you should be able to design. That is the whole point. So this question will be an example of designing two different sequences using some kind of mode control. So step 2 would be simply the excitation table of this. Step 2 would be the excitation table of the D flip-flop. And step 3, start conceptualizing the table based on the previous question. Okay, so let's go to step 2. Write the excitation table. So why the excitation table of D flip-flop is simple, because you can see the next state Qn plus 1 is exactly equal to D, or rather D is equal to Qn plus 1. So what we do is, we have present state. From the state diagram we can define next state, and based on these values we can define the value of D. But we can see that D is exactly equal to Qn plus 1. So whatever is Qn plus 1, we will just copy it there in the corresponding D. So if this is Q2, Q2 will be equal to D2, Q1 will be equal to D1, Q0 will be equal to D0. So I'm just repeating this thing just for your own sake. So step 2 is normal, it is just the excitation table of the D flip-flop. D1 flip-flop is a D flip. Step 3. So we will spend some time on the truth table here. So again we have two modes, m equal to 0 and m equal to, okay. So the first sequence is, this is 7, then this is 4, this is 1, this is 6, this is 5, and this is 2. And this is going to be 4, 1, 6, 5, 2, and then 7. That's the sequence. So next state of 7 is 4, next state of 4 is 1, and so on. This is the second sequence, equal to 1, that is 6, 5, 7, 4, and then we have 1, and this is 0. And here we have 5, 7, 4, 1, 0, 6. So D2 will be equal to Q2 plus D1 will be equal to Q1 plus D0 will be equal to Q0. That is done. Now when m equal to 0, the invalid states were 0 and 3. So that is 0, 0, 0. And when 0 was 0, 1, 1. So these were the invalid states. So for them, we will have don't caps. And when m equal to 1, the two invalid states are 2 and 3. So that is 0, 1, 0 and 0, 1, 1. So again, this will be don't cap. Now with this combinations M, Q2, Q1, Q0, we will make the Q. This way. So start making the K-map. Now, can you answer this question? I want to answer you. I want an answer for this question. The K-map for D2, D1 and D0. The K-map for D2, D1 and D0 will be a 4-variable K-map or a 3-variable K-map. Type your answers in the chat box. Asmita has said 3-variable. Okay. Shubham Davi has said 4-variable. Vishwas 3. Suman 4. 4. Okay. Ashish has said 4. Okay. So the correct answer is a 4-variable K-map. Asmita, Vishwas, you can see that if there would have been only Q2, Q1, Q0, then it would have been a 3-variable K-map. But now, one of the other input that you are giving is M, and that M you are giving it in the present state. That is why now M is also a input. Understood, Asmita and Vishwas?
Yes, sir.
So it will be a 4-variable K-map. If you start from here, this point to this point, you will get 16 combinations. So 16 combinations can be accommodated only in a 4-variable K-map. So start making the 4-variable K-map, which will be like this. So first you copy down the table. I will give you 2-3 minutes to copy this. Once you are done with the table, just write TT done. Actually, this is also like a truth table, but we can say this is a transition table. So if TT is done, just type TT done in the chat box. And those who have copied this can go ahead with the K-maps. So all these problems that we are doing are exam problems. Okay, so please note them properly. When you go through all my slides and notes, exam will just be a formality. It will be very simple. So the difficulty levels that we are seeing are more than what you will get in the exam. So training is always that. Okay, so let's go to the K map. Are you done with the transition table, Shubham?
So that last wala part I didn't get it. Can you please explain it again?
Yeah, so this is the invalid states. These are the invalid states. These are the invalid states. So when m equal to 0, that is in the first sequence, which are the things which are not there? So this is 0 and this is 3. So 0 and 3 are not there in the first sequence, that is 7, 4, 1, 6, 5, 2. In the second sequence, again, we don't have 2 and 3. So these are my invalid states. So I have to account for the invalid states also, no? Because these will also be there in the K map. If you just count whatever is there in the actual table, there are 6 entries here, there are 6 entries here. So in all, 6 plus 6 is 12. But if I want to solve a K map for 12 conditions, I have to choose a 16 variable K, a 16 cell K map. So 16 cell K map with 12 entries you can easily do. But what about the other 4? So first we can make the other 4 don't care. But we should know which those entries are. That is 0 and 3. So for 0, 0, 0, 0, I will enter don't care. For 0, 0, 1, 1, I will enter don't care. For 1, 0, 1, 0, I will enter don't care. and for 1011 I will enter don't care. Did you get it,
Yes.
Shubham? Or
Yes.
so I'll get more clarity on the K map. So see, 000 is actually this first term. If you also consider m in it, this is 0. This is 001, that is 3. 1010 is 10, and 1011 is 11. So in the K map, 0, 3, 10, and 11 will be don't care. And other entries will be as per this, whatever this is.
Sir, in the last question, we took those invalid values as 0. So why don't care in this?
You can take dot 0 also, no problem. 0 means when you take 0, you are handling the lock free condition. You are making the circuit lock free, but that comes at the expense of additional hardware. So your K maps will become very complicated. Whereas when you have don't cares in the K map, the possibility of getting a quad or a octave increases. That is why we are taking K map. So you can choose anything because the question doesn't say lock free. If it would have said make a lock free circuit, then we will have to take 0 in place of don't care. But since nothing is mentioned, we are using don't care. So you can try with 0 also, no problem. But I will first suggest that you copy down this thing and probably then just replace don't cares by 0. That would be better. Okay.
Yes, sir.
You can. I mean, the answer is will still be right. You will still get the same sequence, but at a slightly higher hardware, which will ensure that by chance also this will never go in lock condition. Okay, so let's see the K maps. So first will be the K map of D2. So first will be the K map of D2. In that, you can see at 0, 3, 10 and 11 positions, we will have don't cares, and at others, that is 7 and so on, we will have to write 1 0 1 1 0 1 whatever. So let's see that. Okay. So that is the K map of D2. So like I said, in place of 0, 3, 10 and 11, we will have don't cares, and in other places you will have to see what is M, Q2, Q1, Q0. Accordingly you will fill this K map. So what I will suggest is look at the table and see whether you are getting this K map or not. And if you have any doubts in that, you can ask me right away. And those who are ready with the K map can go for the combinations and tell me what is the answer. Tanish, I will just answer your question here itself about the K map. So if you are listening, just say something.
Yes, sir.
See, in this K map, you can see that you will get an octave here with the help of ones. Can you see that?
Yes, sir.
But in case, if I would have not taken don't care conditions, I would have got zeros here. So instead of a octave, I can now get a quad. So when I go from octave
Yes,
to
sir.
quad, I am increasing the hardware. I will get more terms. More terms means more gates. So that is what you need to understand. Okay, so this is one pair, octave, quad, pair. So there are two pairs, one quad and one octave. So the pairs will give you Q2 bar, Q1 bar, Q0. The quad will give you only two terms, M bar, Q2 bar. Then we have octave, that is Q1, and then M, Q2, Q0. So this is the value of D2. You can see you require a one 3 input AND gate, one 2 input AND gate, and another one 3 input AND gate. Q1 doesn't require AND gate, it can directly go into the OR. So you require a 4 input OR and two AND gates to implement this. Come on, now you solve for a D1. And similarly for D0. So we'll again copy only the second k map, not the first one. Okay, let's go to D1. So again 0 to 1110 are don't 0 to 1110 are 0, 3, 11 and 10 are don't pairs. So this is the K map for D1. So we can see one quad. Then this is the another quad. Then we have a pair. That's it. So we have two quads and one pair. MQ2 bar, M bar Q2 bar, Q2 bar, Q0 bar, Q2, Q1 bar, Q0. And that is going to be the addition of all of them. So please note down this. Next, let's see the calculation of D0. Again, here you have don't care, don't care, don't care, and don't care. And 4, 12, 13, 2, 6, and 14. At these positions, you can see ones in the table. So we'll get one quad here, another quad here, okay. So if you are done with this, just type Kmap done in the chat box. And then start with the implementation of this. Hemant, are you following this?
Yes, sir.
Go ahead with the implementation. Yes. Tanvi, are you following this?
Yes, sir.
Sanjana, what about you?
Yes, sir.
Shruti? Ruchira, are you following this? Okay, Shubham, Sumant, go ahead with the implementations. So let's see the implementation for this. So it is going to be this way. So let me just check whether I have this circuit or not. Let me just check whether I have it or not. Hmm, I think I had it, but I lost it somewhere. Else I would have shown it to you. I'll just search it, and because I have implemented this on the PPT, that means I should have this. I think. Let me just take it out. But in the meantime, you can take the implementation of this. So this is your D2, D1, D0, and this is 0, 1, and 2, and this is your mode control, and these are your three flip-flops at the top, and this is M, this is M bar, then we have Q0, Q0 bar, this is Q1, Q1 bar, and then we have Q2 and Q2 bar. So based on this, you will get something. So you can see here there is no 4 input OR. So what I did here is this is not there in DSA. So I used this 3 input OR to OR the first 3 terms and the second OR to take the fourth term. So in a way to make 4 input OR, I used one 3 input OR plus 2 input OR. So the OR is like this. So this is basically your 4 input OR. That is what you can see here for D2. Okay, copy this. Okay, so if you are done with this diagram, just say done in the chat box. I think you will require some time to draw it. So take another 4 to 5 minutes to draw it properly. And in the meantime, if you have any doubts, just ask me. Unmute and ask. So while drawing also you should be slightly. First you will draw 3 boxes, then you will show B0, B1, B2, and then you will have Q bar and Q. So here like this you will draw. So take these lines down, and then from whatever circuit you get here, you put the line like this inside B2. Okay, so should we go ahead or should we wait? Yes, Shubham.
So wait for 5 minutes.
Okay. Okay, so let's go to the next question. So this is a special type of a counter that is called as a ring counter. So ring counters, you can see some, after I show you the light of the ring, the way in which a ring counter blinks. So this kind of lighting is used at the end of the runway. So this combination is actually used there to indicate that this is the end of the runway. Okay, so note down, design a 4-bit ring counter. When we say ring counter, the obvious question is, Array, what is the sequence? What is the sequence of this? How the counter is expected to count? So that definition is there in this word itself. That is ring counter. So first you note down step 1 and step 2. Here it is directly given 4 bits. So we don't have to apply our brains. N is directly equal to 4. Come on. So this is done. Now let's look at step 3. That is the truth table. So the truth table is pretty simple. What you can see here is that in this case, first Q3 is 0, then Q2, then Q1, and then we have 1. Okay. So this kind of a sequence, when if there are 4 bits and when any one of the bit is only 1 at a time, this type of sequence is also called as a one hot sequence. This is called as a one hot sequence. That means if it's like a 64 bits Q63 to Q0, if only one of the bits from 0 to 63 is 1, then that is called as a one hot sequence. So you can see Q3, Q2, Q1, Q0 is Q0 is 1 first, then in the second case Q1 is 1, then Q2 is 1, and then Q3 is 1. So the next state for this, so this is actually 1, this is 2, this is 4, and this is 8. So basically that is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. If it would have been 5 bit, it would have been 2 raised to 4, and so on. So the next state of 1 is 2. So this is 2. The next state of 2 is 4. The next state of 4 is 8. And after 8, it should again return back to 1. So basically it is 1. Then it goes to 2. Then this comes to 4. Then this comes to 8. And 8 comes to 1. So this is the way in which the counter is supposed to count. And you can see D3, D2, D1, D0 is equal to Q3 plus Q2 plus Q1 plus and Q0 plus. So that is the regular thing. So if you have copied this truth table, just write PT done in the chat box. And the same question remains here. Now, again I am asking you a question here. How many variable K-map will we have to use? 3 variable or 4 variable K-map? Type your answer in the chat box. How many variable K-map do we have to use? 3 variable or 4 variable? Okay, Hemant has written 4, Shubham has written 4, Suman 4, Akhare 4, Yash 4, Gaurav 4. So 4 variable is the correct answer. Shubham, you have asked, but what about don't cares? Yes. So that is my next question now. So my next question is, how many don't care condition, how many total number of conditions will be there? So since you are using a 16 cell K map or a 4 variable K map, we will be having 16 conditions. But out of these 16, how many are defined and how many are undefined? Can you tell me this? Can you type your answers in the chat box? There are in all 16 conditions. Out of these 16, how many are defined and how many are undefined? Four are defined and rest are undefined. Okay. 4 defined, 12 don't care. Yes, Tanish has given the most appropriate answer, followed by Hemant and Omkar. Okay, good. So we will have 12 don't care conditions here. So the possibility of getting an octave is very high. The possibility of getting an octave is very high. Adjay, mute your microphone. So the possibility of getting a octave is very high. So let's see how to fill this. So we will see here that for Q3 there is only one 1. For D3, sorry, D3 there is only one 1. Then there is, for D2 there is only one 1. For D1 there is only one 1 that is in one's place. For D0 we have 1 in the 8th place. So let's fill this. First we will look at D3, that is the K-map of D3. So we have seen that we will get something here 1, 2, 4 and 8. All other positions are don't cares. All other positions are don't cares. So when you are looking at D3, you can see that there is 1 only in the 4th place. 4. In place of 4, there is a 1 here. So you can see here, obviously you will get one octave. You will get one octave, and here we will have 2. So this K map is having 12 don't cares. Now Tanish's question. Can we put zeros in place of don't cares? Tanish, can you answer this question? Can we put zeros in place of don't care?
Sir, we can put 0 in place of don't care. So the numbers will keep repeating between 1 to 4 and 8.
So we can replace it by don't care, but then we will not get an octave. Instead of Q2, we will get an isolated cell, and that will be Q3 bar, Q2, Q1 bar, Q0 bar. So we will have to use a gate, that is a 4 input gate, instead of just directly connecting Q2. But of course, that circuit will be lockout free. It will, lockout condition is taken care of in that circuit. Okay, go for D2, D1 and D0. Go for D2, D1 and D0. So I'm just going to the K map of D2. So you can now again see that in place of 2, we have a 1. In place of 1, 4 and 8, we are having 0, so they are blank. And in all other places, there is a don't care. Correct, Hemant. D2 is equal to Q1. Correct. D2 is Q1. Perfect. So you will have a octave here. So this is your octave. That is your Q1. This is the octave, which is the Q1. Please copy this. Please copy this fast, because these K-maps are really very simple. Yes. Hemant, Omkar, all can go ahead and tell me what is the value of D1 and D0. Now this, I don't know why, but this ring counter question is asked every time in the exam. I don't know why they like it so much, but they ask ring counter every time in the exam. Correct, Suman. D1 is Q0. Perfect. And what about yes, correct. Shubham is also correct. Shubham, try to calculate D0 quickly. Omkar, are you getting the answer? Parth, Parth Thakur, Parth, are
Yes,
you
sir.
there?
Yes,
येतंय
sir.
ना?
Yes, sir.
So what is crucial in counter design is step number 3. If your step number 3 is clear, all you need to do is calculate K-maps and implement the circuit. So let me show you D1. So D1 is this way. So the octave is in this place. Correct. Omkar is correct. D0 is Q3. Niharika Ketki, are you understanding this? Niharika and Ketki, are you understanding this? Are you there? I think we are not there. Okay, anyway. So this is your Q0 and D1 is Q0. And let's quickly see the calculation of D0. So here you have an octave at the lower part of the K-map. Hemant and Omkar, why don't you start implementing the circuit? It will be really very easy. You can see that there are no gates involved at all.
Yes, sir.
So this is the K-map. The position of don't care don't change. Only the position of 1 is changing. And in a sequence when only there is only one out of the so many bits which are there in that sequence. That sequence is called as a one hot sequence. It's called as a one hot sequence. So these are like gate questions. They will ask you, they will give you a series of bits and ask you which of the following is a one hot sequence. So you should be able to say that time that this is a one hot sequence. Okay. So let's go to the circuit of this. So this is very simple circuit. First you will draw 3 flip-flops D0, D1, D2 and D3. This is Q0, Q1, Q2 and Q3. This is D0, D1, D2 and D3. So you can see that D1 is equal to Q0. That is why Q0 is directly connected to D1. Then we have D2 directly connected to Q1 and D3 directly connected to Q2 and Q3, that is D0, is equal to Q3. So these are the conditions that we have found out D1 is Q0, D2 is Q1, D3 is Q2, and D4 is, sorry, D0 is Q3. These are the terminals. So that is what we have done. Now, what I want you to tell is, if you implement this circuit as like this in DSCH, it will not work. It will not work. The problem here is with the reset. The problem here is with the reset. So actually what happens is that the moment you reset, the output of all the flip-flops becomes 0. The output of all the flip-flop becomes 0. So here we have it. Here we get 0, here we get 0, here we get 0, and here also we get 0. And this 0 comes here. So the output again becomes 0. So what happens is that the outputs of this counter will always be 0, 0, 0 only. And there is no way to make it 1. That is the problem. So that is the reason why. So this diagram you can draw like this in the exam. But as far as the lab is concerned, it has to be this way. It has to be this way. Now, what is the change in this? You can see that Q0 is still connected to D1. Q1 is still connected to D2. Q2 is still connected to D3. And Q3 is still connected to D1. So those connections are absolutely same as per our K map. The only thing is the reset will be given only to the first flip-flop. The reset is given only to the first flip-flop. Then only we will get the sequence here. So first we should get 0, 0, 0, 1. Then we should get 0, 0, 1, 0. Then we should get 0, 1, 0, 0. And then we should get. So this is what we are expecting. So this is the actual implementation of DSCH, but in the exam you will draw the previous one. That is, you are resetting everything together. This is just a thing that you have to do in DSCH. So let's look at that. So I will show you both. This is what we actually designed. That is, reset is going to everybody. But now if you try to simulate this thing, see, if I reset it, all output becomes 0 and there is no way you can put a 1 inside the loop because we want a 1 hot sequence. But the moment I open the reset only the first one, so please note these points down. Okay, this will not be there in any book. It is just purely by experience. So here when we try to reset when we remove this, just a minute. So you should be able to see this now, that the 1 goes inside. Let me just I don't know why it did not got saved, but yes. we can still put the. So please start drawing this. In the meantime, I'll just construct this thing. So first is let's see what I'm doing. I'm just taking the outputs properly from the corresponding places. So my last one is actually Q3. Then we have Q2. Then we have Q1. And then we have Q0. So I'm just simulating this thing. So I just lost track of the feedback here. So you can see this counter here now, how it moves. That is, first is you get only one output one at a time. So this is called as a one hot sequence. Are you all able to see this? Hemant, are you able to see this?
Yes, sir.
Yeah. So you can actually reset only the first one, but just for the sake of it, you can show that okay, everything is resetted before. So this is called as a ring counter. The complement of this is called as a twisted ring counter. So, but anyways, we will now take a 10 minutes break. Uh, so you can implement this thing in your book or your DSCH. I'll just leave it like this. So we'll be back at 11:25. In the meantime, if somebody has doubts, they can just ask, no problem. Okay, Shubham, I can see that. You have also connected a display, right?
Yes, sir.
So, are you getting 1248 on that counter?
Sir.
It should display 1248 like that.
Yes, sir. I'm getting it.
Okay. So let's go ahead. So take down the next question, that is design a 3-bit twisted ring counter slash Johnson counter. So twisted ring counter is also called as Johnson counter. So sometimes they may just say Johnson's counter. So it is one and the same thing. It's the same twisted ring counter only. Design a 3-bit. So they can say 4-bit, 5-bit, 6-bit, whatever. So it doesn't matter. Now here, calculation of number of flip-flops. So here n is, let's check. So here slight small mistake here. This should be n equal to 3. And here also it should be n equal to 3. Because they have said 3-bit. If they would have said 4-bit, then this 4 would have been right. Otherwise, this is 3 only. So I have just made it 3-bit to save the number of calculations. So write step 1 and step 2 quickly. Just write step 1 n equal to 3. Step 2 excitation table of D flip flop. Just you have to note that 2n plus 1 is the same as okay. Let's go to the step 3, that is the truth table. So you can see from here, that is in the truth table, present state starts with 0. Then you insert a 1 from this side, that is it becomes 1. Then you insert one more 1 from this side, so it becomes 3. Then you insert one more 1 from this side, so it becomes 7. Then once all are 1, then you insert 0. So this again becomes 6, and then this becomes 4. So basically here after 0 we want 1, then after 1 we want 3, after 3 we want 7, after 7 we want 6, after 6 we want 4, and after 4 we want this to come back to again 0. So that is why this is going to be 0. So you can see here which states are not defined. 2 is not defined, that is 0, 1, 0. And you can also see 5 is not defined, that is 1, 0, 1. So the next states for that you can consider it as don't care, or you can also consider it as 0. It's your choice. But consider it as don't care in this thing, then I will tell you how the circuit comes out to. So there is a small relationship between ring counter and twisted ring counter. So this is the transition table. Come on, copy it quickly. I have also shared the link to upload IEEE paper and the presentation. Both have to be in PDF format, and the presentation can be in PPT format. So you can do it by 17th October, that is by next week. So once you have copied this truth table, just say TT done. You don't even have to write this, you can just write step 3. Okay, D2 is Q1. Yes, that is right. Calculate D1 and D0. Okay, let's see the calculation of the QMAP. So there are two conditions which I don't care. One is 5 and other one is 2. So So you can see those don't cares here, and then you have your 1. So as Yash said, D2 is Q1, that is right. Yes, D1 is Q0, correct, yes. And calculate D0 now. Others can confirm whether your D2 K map looks like this. Yes, your D2 K map looks like this only, na?
Yes, sir. Yes, sir.
Okay. So it's a pretty simple K map. The K map is just key variable, that is 8 cell, and in that there is one for, and that will give us D2 equal to Q1. Okay, D1 is like this. Yes, your D0 is, I think, not correct. Yes, Omkar, D0 should be
Yes,
Q2 bar. Check it. Yes.
yes, sir.
So that is the change, right? Suman also got D0 is Q2. So in a ring counter, one output is connected to the next input. But in a twisted ring counter, the last output is not actually connected to the first input. It is the complement of that is connected to the first input. So that is the only change. So D1 is Q0 and D0 is Q2 bar. D0 is actually Q2 bar. So the implementation of this would be you save ring counter as it is, save ring counter as twisted ring counter, and in that for the last flip flop Q is like Q3 or Q3 is connected to D0. So Q3 bar only you can connect it to D0, but that would be a 4 input. So you can remove one flip flop also and simply connect your Q2 to D0, Q2 bar to D0. So this is the implementation. So here we have D0, D1, D2, D0, Q1, Q2. This is Q2 bar. So now I am connecting Q2 bar. So D0 is equal to Q2 bar. D1 is equal to Q0. That's the only change. So I'll just run this for you. So this is the twisted ring counter. Let's reset it. So you should be able to see this. I'm just keeping the pins on. Just slow the clock. Clock is too fast. We'll start with 0. Now we will get 1. Just see. Then again when the clock becomes so draw this circuit. Now all three will blink. Now Q0 will become 0. Then Q1 will become 0. And then Q2 will become 0. There is a small latency, but anyways, it's there. Correct, Hemant. You have got that. Now just see the implementation of this. Yes. So Shubham, I think all you had to do is delete some flip-flops and get this, right?
Yes, sir.
So this is called as a twisted ring counter or a Johnson counter. Even this kind of lighting is used in the runways. So slowly one light blinks, then the entire line is one at one point of time, and then again the light starts dimming from one end. So these kinds of lights are used still on runways at night to mark the runway. Of course, LEDs are not used. There are huge flashlights, and they are controlled by using controller. So if you have finished drawing this, just write done in the chat box. So I hope you are liking this designing and implementing thing. I mean, this is what you should do, because only theory becomes a little bit boring. Okay. So let's go to the next part. So this was our actual circuit that we were just seeing right now. Right, next. Shift registers. Shift registers. So when it comes to shift registers, there are some types, that is SISO, serial in, serial out. Then we have serial in, parallel out. Then we have parallel in, parallel out, and then we have parallel in, serial out. Shift in, shift out can have left shift and right shift. It can have left shift or right shift. That means you can shift the data from one side to another. So next semester, I think you have not yet done uh, microprocessor, but in microprocessor there are some instructions called as rotate left and rotate right. So to implement these instructions, you should have a hardware which is something like that you are seeing on the screen. So that is basically your shift registers. Shift registers are also used for temporary storage of data. That means, let us say you have a LAN controller. Now, the LAN controller is the bits are coming serially inside. The bits are coming serially. But your internal bridges which are there on the for the microprocessor, let's say there is a 64-bit data bus. So it reads 64 bits at a time. So you will use 64 clocks to get your 64-bit data inside a register, and then you will read 64 bits in one go. So that kind of operation is called as serial in and parallel out. Many times when you want to send the data, you are not receiving, you are sending the data. So your data is parallelly loaded into a shift register, and then it is serially, it is sent out. So that kind of operation is called as parallel in and serial. And many times one bus communicates with another bus in the form of parallel in and parallel out. So data is stored in register and it needs to be loaded into another register. So this can be done in a parallel fashion. So these kind of registers, that is serial in, serial out, serial in, parallel out, parallel in and parallel out, parallel in and serial out, are used to perform different kinds of data transfers between two systems and within the system also. So generally our LAN cables will have serial data transmissions, whereas the address buses inside the computer system will do parallel, will transmit everything parallelly. Parallel transmission is faster and serial transmission is slower. So when we say like this, when we say my speed is 6 Mbps. So when everything is capital, it means megabytes per second. Megabytes per second. But generally, if you see, you are on a computer, if you just click on your LAN setting, you will see something like this 6 Mbps. BPS is small. So this is called as bits per second. Just different notations. So remember between this and this, they are not the same. Capital M, capital B, capital P, and capital S is megabytes per second, and M capital and BPS small is megabits per second. So serial registers, we have these three things. Now you can see here, this is a very simple thing. You can give a data here, one, whatever you want, and it will flow through the flip-flop, and that you can observe on Q3, Q2, Q1, and Q0. Since the data flows from, it is a shift right, so it will go from, I'll just show you that. So serial in, serial out. There is something that was interesting. It did not get saved somehow. So this is actually shift left. Sorry for the so let's see the circuit first. So I'm just resetting this. So you can see that initially everything is 0. But the moment I make this 1, at every clock you will see now serially all what is coming inside is 1. Now I can change this here. I can change the sequence that I want. So whatever I am feeding, I am getting it. So what you should observe is that first Q0 changes, then Q1, then Q2, and then Q3. So that is why you are shifting towards the left. You are shifting the data towards the left. So you can see that the bit is going to change from Q0, Q1, Q2, and then Q3. Changes from Q1, Q0, Q2, and then Q3. So that is why this operation is called as shift left operation. This operation is called as shift left operation. Now I can see that there is some latency, so I'll just lower the clock so that you can see. Okay, so you can see that the 1 is coming from the Q0 side, then Q1, Q2, and then Q3. And the moment I make it 0, the 0 comes from Q0 side. So shift left means when the bits are traveling from right to left. When the bits are traveling from right to left, that is shift left. So I fed one bit inside and then I'm feeding all 0. So this is your shift right, sorry, shift left. And the second one is actually shift. So please copy this diagram. So when you want to shift right, you are giving the input on this flip-flop, the last flip-flop. Many times what happens is this shift left and shift right are these terms are used interchangeably. Now many of you will have a confusion actually. I'll tell you that also. And we'll just highlight that point. So even when I was a student, I had this confusion. And then I thought that it really doesn't matter where it is. Here I am writing shift left. You might feel I am writing here shift left. So we saw that if I look at this Q3, Q2, Q1, Q0, the bits are entering from this side. So they are going from right to left. That is why we are calling it as shift left. The bits are moving leftwards. That is why we call it shift left. But here, if you see the diagram, if you look at the flip-flop, you are actually giving the input here. You are actually giving the serial input here. Just because this was D0, D1, D2, and D3, actually your bits moved in this direction. Actually, if you look at the circuit, the bits moved in this direction. But you should understand that this was your MSB and this was your LSB. So whenever we write the bits, we write MSB on this side and LSB on this side. And then we say, if this is a register, then if the bits move this way, then it is going to be left shift. If the bits move this way, it is going to be like right shift. So in the circuit, though you are entering the bits from the left side, the bits might move from left to right through the flip-flops, but as far as the final output is concerned, that is Q3, Q2, Q1, Q0, it seems that the output is moving from right to left, that is leftwards, and that is why this operation is called as shift left. So this is your register actually Q3, Q2, Q1 and Q0, and your bits are entering at Q0, that is here. So this is where your bits are entering, that is Q0, and from here they are coming out, that is at Q3. So though the bits are moving in this direction, actually through the flip-flops from D0 to D3, we are looking at output that is from Q3 to Q0. I hope this has solved the query in your mind. Yes, any doubts? Please ask. Okay, let us go to the next circuit. Actually, there is nothing in this flip-flop. The flip-flops are just connected one after the another with input given to the first flip-flop. So actually speaking, a register is just a combination of flip-flops, and flip-flops are a combination of gates. So if you want to build like a 64-bit register, it will require at least each flip-flop. You will require 64 flip-flops, and each flip-flop will have a JK flip-flop inside it, which is operating in D mode. So there will be around 8 or 9 gates, and each gate will have around 6 transistors. So 8 9 is 72 into 64 of them. So that's a huge number of transistors for a single 64-bit register. Okay, let's go to the next one. So this was my SISO, SISO, serial in, serial out type of register. Now let's look at serial in, serial out, but shift right. Shift right means bit should flow in this direction. That means the data through the flip-flop should flow in the other direction. So that is why you can see here my data input is given on now D3. My data input is given on D3. So I'll get Q3 first. The output of Q3 is given to D2, which gives me Q2. The output of Q2 then goes to Q1, that is D1, gives me Q1, and Q1 is now going to D0, which will give me Q0. So this is how it is. This is D0, D1, D2, and D3. So please copy this. So these are just direct implementations. There is no design as such involved in this. Though we can design this, there is no problem, but we know the next states, no? So we can design. But we are not sure what the bits are, what that data input is, that we are not sure. We don't know what is that data input. It can be anything. It can be 1 or it can be 0. Okay, have you implemented this? Hemant, have you drawn this diagram?
Sir, 2 minutes.
So I hope you are understanding this shift left and shift right. When you are giving the input on the leftmost side of the flip flop, it is actually shift left, and here we have shift right. I am not changed this, I think. Just a minute. You can just take it like this, that if serial in is on leftmost side, it is shift right. Actually speaking, it is shift right. So let's see the circuit for shift left. That is the other way around. So you can see now the bits are going towards the right. The bits are going towards the right. I'll reduce the frequency of the clock. I'll just make it. So bits are shifting towards the right. So draw this diagram. And if possible, you implement it directly. Vishwas, are you there?
Yes, sir.
So these are all direct implementation. So there is no much designing. So if you are done with this, just write done in the chat box. Now we want something called as bidirectional shift register. That means we should be able to shift left as well as right, both. So we should be able to do that. That means there has to be a provision to connect Q1 to D0 and the other way around also. So there has to be a provision to do a connection that we saw in shift left as well as shift right. So let's check that out. Should I move ahead in this or should I wait?
Hello, sir. Hello,
Yes,
sir.
yes.
Is this only a one-time operation or does it repeats? Because I implemented it on D schematic.
Uh,
It runs from left to right, but then it
it,
doesn't means
it
I
is
have
not one.
to
No,
turn
no.
off the
Okay, so I'll tell you what is happening. It is still shift. It is not one time. What you are doing is initially you are resetting, right?
yes,
Yes, initially you are resetting, na? So let
yes,
us say we have clock 1, 2, 3, 4, 5, 6, and 7. Let's say it is like that. Then in clock number 1, if you are giving 1, then at the output you will get 1. At clock number 2 also you are giving 1, then you will get 1. At clock number 3, if you are giving 0, then you will get 0. So what happens is, what you might be doing is, you might be keeping data input 1 only, right? So try to change the data input. That change will reflect on the output. So your answer, so the question was it one time? No, it is not one time. Whatever you feed in serially will come out serially. If you are feeding ones continuously, you will get ones continuously. If you are feeding zeros, you will get zeros continuously. Have you understood this, Yash?
yes, sir.
And if in between, if you change 1 0 1 0, then you will get that sequence at the output, that is 1 0 1 0. And the change has to be created at data input.
Yes, sir, got it.
Yes. So let's go ahead. That is serial in parallel out shift register. So you can see serial in parallel out are is something similar to the I think it was the left shift register. It was something similar. So what you do is we have clock number 1, 2, 3, 4 and 5. So at clock number 1 we have serial in, then again at clock number 2 also data is coming serially in, at clock number 3 also data is coming serially in, and at clock number 4 also you are getting serially in. So here you get the second bit, first bit, third bit and then fourth bit. At the fifth clock you will get parallel out. So first three clocks, clock number 1 to 4 will be used for serially inputting the data, and clock number 5 will be used for outputting the data. So actually this serial in and parallel out operation for a 4-bit shift register, this operation SIPO will occur in 5 clocks. Will take 5 clocks. Four for serially inputting the data and 1 for parallelly outputting the data. So draw this diagram and note down this thing whatever I have written. If it is a, so now I am asking you a question. If it is a 64-bit serial in parallel out shift register, in how many clocks will I get the output? If it's a 64-bit serial in parallel out shift register, in how many clocks will I get the output? Type your answer in the chat box. Sixty-four clocks? No. It has to be 65 clocks. 64-bit means no, not 7 clocks. 64 bits means there are 64 flip-flops, and 64 flip-flops means you will require 64 clocks to input the data to completely fill the register, and one additional clock to output everything parallelly. So for a 4-bit, if it was 5 clocks, for a 64-bit, it would be 64 plus 1, that is 65. Yes, any doubts in this, please ask. So circuit wise, it is similar to a serial in serial out register, but at the fifth clock state, we are reading all the 4 bits at a time. So till the first 4 clocks, it is acting like a serial in serial out register, but at the fifth clock, we are reading all 4 in one go. Okay, let's look at the next one. Parallel in parallel out shift register. parallel in, parallel out shift register. That means what? One clock I require to load the data, and one clock I require to read the data. So in one clock I will load I0, I1, I2, I3. So I will load all of them parallelly, and in another clock I will read that data. So let's see the circuit. It is CIPO. So you can see here, in one clock I am loading the data, in another clock I got here Q0. So this is D0, D1, D2, D3. So I got here Q0. If I load here, I got this thing here. So whatever I load in one clock, I get it in the next clock. So this is your basically your parallel in, parallel out register. Parallel in, parallel out shift register. Come on, draw this. So I will share all these schematics with you, but unfortunately in the exam you will have to draw this. So you should know how to draw it. So we have seen SISO, serial in, serial out, serial in, parallel out, parallel in, parallel out, and parallel in, serial out is also very simple. So parallel in, serial out is exactly the reverse of serial in, parallel out. That is one clock we require to load the data. One clock we require to load the data, and 4 clocks we require to output the data. That is PISO, not PIPO, parallel in, serial out. So please note in this figure, this is your LSB and this is your MSB, and here this is the MSB and this is the LSB. That is why Q0 LSB is connected to the output of the LSB itself. So this is D0, D1, D2 and D3. Okay, let's go to the next one. This is parallel in, serial out. Parallel in and serial out. So before you start drawing, let me just again explain you the circuit. So this is the parallel in, serial out circuit. You can see here, if I simulate this thing, I'll just reset it. Okay. So initially all the outputs are zero. Initially all the outputs are zero. So here there is a special button here. Can you see? Shift and right. So whenever there is a zero, we are doing a right operation. Wherever there is a zero, we are doing a right operation. So you can see, and whenever there is a one, when we put one here, it is going to be a shift operation. So this is one. You can see that the lower AND gates get enabled, and when this is zero, you can see the upper AND gates will get enabled. Obviously, when one AND gate is enabled, the lower AND gates will automatically get disabled. So this is for the simple reason that when you are reading, you cannot write, and when you are writing, you cannot read. That means if you are reading a Word document, at the same time you can't do a delete operation. You cannot change something in that place. So it is something similar. When write is on, reading is disabled, and when reading is on, writing is disabled. So read and write cannot occur at the same time. So this NOT gate ensures that when one is on, the other one is off. Now you can see that when this shift operation is not in, when this shift is zero, that means what? Right bar signal is on. So we are now in a position to write something. So when I want to write something inside, write means what? I want to input the data inside. So you can see I gave here one. I gave here one. And I got one at the output. You can see here. I0 is 1 and Q0 is also 1. I0 is 1 and Q0 is also 1. Similarly, if I make this I3 1, my Q3 also became 1. If I made this 1101, if I read it I3, I2, I1, I0, I will get Q3, Q2, Q1, Q0 also as 1. So what we are actually doing now, what we are actually seeing is what is actually written into this particular register, what is written inside. That is what we are seeing. Now I want to clear this register. Now I want to clear this register. So I want to send whatever is stored inside outside. So I now enable the shift button. So you can see here the shift LED will glow now. You can see now the shift LED has glown, and now the bits are getting shifted. The bits are getting shifted. So whatever we are entering inside, that gets shifted serially out. Whatever we are entering inside, that gets shifted. If I am giving here, you can see 1100. Now if I give again 00, that thing will get shifted out. So basically this is a parallel in, and then you can do a shift. So this is the diagram for the parallel in and serial out. So I can go back to this diagram here. So in this diagram, this is my D0, then we have D1, this is D2, and this is D3. So when this button is 0, that time you are doing a write. Write means parallel in, and when this button is 1, you are doing shifting operation. Shifting means serial out. So during 1 you are doing parallel in, when you are keeping this as 1, it is serial out. So either you can take a screenshot of this, or anyways today I'm going to send you everything. So you can just understand what is going on, that's it. So these gates, the lower gates are actually used to feed Q inside. You can see here, this is Q0. Q0 comes here, and if this gate is enabled, this is 1, 2, 1, 2, 1, 2. If gate number 2 is enabled, Q0 goes to D1. So Q0 goes to D1 means what? The data travels from D0 to D1. If 2 is enabled, then D1 will go to, then this Q1 will go to D2. If D2 is enabled, this 2 is enabled here, then Q2 will go to D3 and so on. So basically, if you enable the second AND gate, you will get serial out. And if you enable the first one, AND gate, you will get parallel in. So here we will take another break of 5 minutes. Those who want to complete this can complete this in that 5 minutes, and we will resume back at 12:35. 12:33, sorry. And in the meantime, if somebody has a doubt, can unmute and ask. I'm just sending you the files here. Then I will send you the parallel ones also. So just sending the circuits to you for your reference, so you don't have to break your head in actually drawing everything. But yes, in the end, you have to have a practice of drawing. So to those who are still drawing can just see the schematic, download it and open it in your DSCH folder. You can open these files and check for yourself. Okay, so let us start. So the next counter is bidirectional shift register. So all this comes in synchronous counters only, but synchronous because of this clock. Everything is clocked simultaneously. So you can see here that this is my data in. So see again my flip-flop number and gate 1 and 2. So if AND gate number 2 is enabled, if AND gate number 2 is enabled, enabling is done with the help of this. So if I enable this, if I make this 1, then this gate will get enabled with 2. So my data so D will get D in will come here and it will give me Q. Now 2 is enabled. So again this Q0 will come here at B1 and that will give me Q1. Q1 will come here at 2 and that will come to B2 and here we will have Q2. So Q2 will come here to B2 and then finally this thing will come at Q3, Q2, Q1 and Q0. That's it. If so, if AND gate 2 is enabled, the what we will get here is a left shift. So data will flow like this: Q0, Q1, Q2, and Q3. Naturally, because D0 will get enabled first, then D1, then D2, and then D3, which will give me Q0, Q1, and Q2, and Q3. So this is the direction in which the data will flow. If AND gate number 1, all 1 number AND gates are enabled, then the data will flow in the other direction. How? Because if 2 is disabled, what happens here is that this data input, you can see here, initially everything is 0. So this becomes my data input. This is my data input. This data input, if you can trace it, it goes to this AND gate. So I get D in here also. So I have got D in here, and that same D in is also given to the one of the AND gates here. So D in goes to D3, which will give me Q3. So Q3 is connected back to D3, and then Q2 is connected back to D1, and so on. So it is connected backwards. So now the data will flow from in a reverse direction, that is from Q3 to D2, Q2 to D1, and then finally D1 to D0. So if you want, I'll just trace the connection. First, you can see this D in. I'm just going to make this diagram dirty now. This is my D in. If you can trace this line, it comes into this. So if I enable this one, this D in will come here. So data input you are giving on the last flip-flop. That is what you did when you were trying to do right shift. So this Q3 you can see here, this thing goes into this flip-flop, and this is connected to D3. So we had two flip-flops previously. The output of one was going as input to another. So that connection we have achieved through the AND gate, through this. Similarly, for the second flip-flop also you can trace the same connection, and that is going to come to D1. So that is how this circuit is. So let me just open the digital schematic for it, and let's try and find out that. So this is my bidirectional shift register, and let's see this. So I'm giving the data here. I'll reset this. So you can see that data is coming from Q3, then Q2, then Q1, and then Q0. And yes, now you can see, since my data in is 1 only, I will get continuous ones at the output. But if I make data 0 now, if I make data 0, you can see that Q3 becomes 0, then Q2 becomes 0, then Q1 becomes 0, and then Q0 will also now become 0. So now you will get continuously zeros at that. Now if I want this to happen the other way around, if I want this to happen from Q0 to D3, so I will just use this. So this is shift left. So now you will see data bits coming from Q0 side and going to Q3. Check it. So you can see Q0 is 1, then Q1 becomes 1, then Q2 becomes 1, and then Q3 becomes 1. And since the data in is 1, you are continuously inputting ones from Q0 side. If I start inputting 0, now you can see Q0 will become 0, then Q1 will become 0, then Q2 is 0, then Q3 is also now will become 0. Yes, it has become 0. So you are putting the data from the LSB side inside this shift register. LSB side means it is leftwards. The data is entered leftwards. That is why when this button is 1, you can see this left LED is glowing, and when I make this 0, right LED glows. So when it is 1, it is left shift. When it is 0, it is right shift. So again, you can see that this is right shift, and now if I want left shift, let's make this thing 0. See, now from the left side it is going to shift. So I want many times left shift, and so because when you have done programming also in C, you have these instructions. Many times you have to rotate an array. So how to implement this instruction at the hardware level? To support this instruction, you should have such kind of facility at the hardware level. So if you write in programming, if this is the sequence, shift left. If this is the sequence, shift right. So this shift left and shift right signals are coming from the program, and accordingly the circuit inside will do shift left and shift right, and this Q3, Q2, Q1, Q0. So when you say C out or you say printf, this printf and CA out command actually read the values at Q3, Q2, Q1, Q0, and it displays that same thing on your screen. So we are doing the backend of all programming, that is the hardware part of it. So we know now how these instructions are supported with the help of different kinds of registers. Okay, so copy this thing. Any doubts in this? Please ask. So I think I will keep this circuit and I will remove all this things so that so I cannot use a register only for shift operation. I cannot use a register only for write operation. I want everything in the same register. So of course the control logic has to be there. Now if I go one step ahead and say I don't want uh, serial operations and parallel operations to be separate. I want everything to be in one only. So that register is called as universal shift register. Universal means it gives you all kinds of operations. So that is the next one. So I'll just drop the code for this in the chat box. So I'm just saving your effort of drawing by giving me the schematic files. And the next one is universal shift register. Universal shift register. So here we have three class of AND gates. This is 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Now I want you to observe one thing here. You can see AND gate number 2. You can see AND gate number 2. If you observe AND gate number 2, on AND gate number 2, you are giving your parallel inputs. Parallel inputs. That means if you want to do parallel in, you have to enable AND gate number 2. If you want to do parallel in, you have to enable AND gate number 2. Okay. You can see on AND gate number 1. You can see AND gate number 1. First AND gate, if you see the flip-flop, this one, this AND gate, here you are giving your serial in data. If somehow I enable this AND gate number 1, this data will flow to the OR gate and it will come to flip-flop D0. This is D1, this is D2, and this is D3. So it will come to D0. D0 will give an output Q0, and Q0 will come inside this. Q0 would come here. Now the Q0 output will flow through this OR gate if I enable this 1, and it will go to the Q0 becomes D1. Similarly, here we have Q1. Q1 can flow through this and come here, and that will become D2. And similarly, here we can get Q2. Q2 can flow through this, and that will be equal to D3. And finally, here we have Q3. So Q3 can go back if you want, and can be used in rotate kind of operations. So that is what we can see here. So AND gate number 1 we can use for shift right operations, and AND gate number 3 we can use for shift left operation. We can use for shift left operation. So if you look at any register, SISO, SIPO, PIPO, and PISO. So this parallel out is just observing the outputs. Actually, you are not doing anything, but you have to take effort to do serial in, to do serial parallel in, and to see serial outs. So to output the data serially, you require 4 clocks. To input the data serially, you require 4 clocks. And to parallelly input the data, you require just 1 clock. Parallel out operation is just the observation operation. So that is why this AND gate number 1 supports parallel in PI. AND gate number 2 supports serial in, and AND gate number 3 supports serial out. So serial in, serial out, I will say both of them can give us, depending on how you are outputting. You are outputting from left or right. So this is what this universal shift register actually does. So if I give here 0 0, let's say if I give here 0 0, then on this line we are having a 0, and here also we are having a 0, here also we are having a 0, here also we are having a 0, and here also this is 0, this is 0, this is 0. So AND gate number 1 and 3 are disabled if S0 and S1. If this is 0 0, AND gate number 1 and 3 are disabled. 1 and 3 are disabled means what? That you cannot enter the data, you cannot enter the data serially. Serial in and serial out is closed, but AND gate number 2 is enabled. Why? Because this is 0 0, this is a NOR gate, so here you will get 1. So like read and write, when you are operating serially, your parallel functions have to be out, your parallel functions have to be disabled, and when you are operating parallelly, your serial functions have to be disabled. So here AND gate number 2, this will become 1, this will become 1, and this will become 1, and this will also become 1. So whatever you input here, let's say if you input 1 0 1 0, then 1 1 will give me 1 here, so that will give me a 1 here. Then 0 1 will give me 0, this will give me 1, and this will also give me 0. So what will happen? The moment I clock, this 1 would come here, this 0 would come here, and this 1 and this 0 would come here. So basically this is a parallel in kind of a operation. So this is parallel in. So you can use this combination for parallel in. Similarly, you can check what happens if you give 0 1 here. If you give 0 1 here, this will be 0. So all parallel operations will become disabled, and only serial operations will start. So serial means it can be either 1 is enabled or 3. If 1 is enabled, it will be shift right kind of operations. If 3 is enabled, it will be shift left kind of operations. So if you have 0, 1, let us say 0, 1 means we have shift right operations, and 1, 0 will be shift left. And what about 1, 1? What if both are 1? What if both are 1? Both are 1 means there will be no change. There will be no change. So this is what actually happens inside this 4-bit universal shift register. So please draw this. I think I have posted this circuit. No, I'll post this circuit also for you. Yes, so I have posted that circuit also, but I want you to note down these critical points because this is slightly more important. Parallel in, shift right, shift left, and no change. Yes, any doubts in this? So you can see the AND gates facilitate the enabling or disabling of AND gates facilitate to choose a specific function during operation. So that is what this shift register is all about. So generally in all microprocessor designs, we will go for always universal shift register. We will not go for just shift left or just shift right or just parallel in parallel. We will not go for that. We will always go for universal shift register. And the mode of operation you can choose by controlling S0 and S1. Okay, so it's 1 o'clock. So that's it from my side for today. Next time we'll start with Moore and Millie machines. Just a warning, please revise all your excitation tables of flip-flops and please revise counters which we have solved in class, especially how transition tables are generated, and how the state diagrams are made. This you have to understand because the next part talks about minimizing the state diagram. So that is a slightly higher concept. We have seen minimization of logic functions. Now we are going to do minimization of states. Some states might be completely redundant, so we may have to reduce it. So in the next week we will do that. So that's it. Let me download the attendance sheet. Don't log out. Okay, so your attendance is downloaded. So you are free to log out and have your lunch.